start out with any questions?
Are we doing how do the test corrections work? Are we bringing it home with us, or are we doing?
Yeah, I'll hand it back
Oh,
before the
okay.
end and.
I
we'll
thought we
get-
were doing it here, that's why I was confused.
Oh, no, test corrections, that's a at-home thing.
Okay.
Yes?
I've missed 2 quizzes and the test. I don't have time to make it up before class, cause I have another class that ends at 2:45, so how can I come?
All right, so at the break, let's talk.
Okay.
No other questions? We last left off.
We should. No, last Thursday. I thought we did.
Is there a question?
No, I was talking about the lab, sorry.
Oh, okay. So it seems like we last left off a couple weeks ago with just some basic definitions that we'd be working with, one of which is the term work. And then we have kinetic energy. Potential energy. We had rest energy also, but that was just sort of a side note, so I'm not gonna put that down right now. Conservative force and non-conservative force.
Bless you.
So work is force times displacement, and part of what we talked about is the fact that it is the first time we're actually really covering multiplication of vectors. And if the force and displacement are parallel, then you just multiply the numbers just like normal. So if I have a box that gets pushed 3 meters with a 5 Newton force, the work done is 5 newtons times 3 meters, or 15 joules. That's a capital J. If we have a box that's going to be going 3 meters, and you're pushing against it, trying to stop it from going that distance. So this is the bus heading for the orphanage, and you're standing in front of it, sort of trying to block it, and mildly succeeding. Then the work, they're in opposite directions, so we're doing negative work. So it'd be negative 5 newtons times 3 meters, negative 15 joules. Or, this assumes that to the right is positive. But if you assume that to the left is positive, then the work would be 5 newtons times negative 3 meters. And it's still negative 15 joules. In this first case over here where we have positive work, we're putting energy into the system, we're going to make it go faster. In the system over here, we are taking energy out of the box, and ultimately it'll go slower. So conceptually work is how you will do one of 2 things that will change the type of energy from one form to another, like from kinetic to potential and potential to kinetic, or it will put energy in or take energy out of the system. Sort of the conservative, non-conservative force. Conservative force will change the energy. Let's see, conservative force causes conservative work. Which causes energy to change types or transform from one type to another. And non-conservative force will just change the overall amount of energy. Kinetic energy is the energy of movement, potential energy, the energy of position. And I think that's a very quick recap of what we've done. Oh, I guess there are a couple other bits and pieces. Conservative forces. Name the conservative force.
Gravity.
I'm gonna nitpick. Name the conservative force.
Magnetic.
Okay. I'll accept magnetic. Why am I not accepting gravity?
I don't know, it's in my notes. You said it last time, so I was just throwing it out there.
What's wrong with gravity as the name of a force?
Because it can change wherever you are.
Say it again?
The influence of gravity can change wherever you are.
I was about to say no, but let me make sure I heard it.
Influence of gravity can change wherever you are.
It can, that's not the reason why, some of the wording you use hit upon it, exactly what I was looking for here. However, not all of it.
Okay.
So anyone want to pull out part of what Latoya said? And
Are you wanting us to say weight?
oh, there we go, I'd accept that. What's the difference between gravity and weight?
Your weight can change.
Okay.
So maybe the conservative force is a collision?
No, weight is an example of a conservative force.
Okay,
Collision would be an interaction between two things.
okay.
Gravity doesn't have gas? Or weight is mass.
What is gravity?
No.
It's the pull from the Earth's core.
Yeah.
Oh, that's only part of it. And I would accept it probably pull from the earth. I would accept it also as a conservative force. What is lowercase g?
Acceleration due to gravity.
Ah. What is little w?
Mass times gravity.
And there we go again. We're use the term gravity without defining what gravity is. What is little g?
Acceleration due to gravity.
Why is it not gravity?
Because we pulling down, well, I don't know, because I'm not able to define gravity.
Yeah, I mean, gravity is a huge topic, of which we can look at a tiny bit of it, and it's the force due to gravity. There's acceleration due to gravity. There's the gravitational constant. There's the warping of space and time because of gravity. Gravity itself is not a force. That's the issue there.
I got you.
It's force due to gravity, or weight, or gravitational force I would accept. But gravity itself is a very huge, broad topic, of which force is only a tiny bit of it. All right, so we have gravitational force, or weight, and I'll put F sub G there, because we do have two types of gravitational force we deal with. They're really part of the same thing. W is when you have an object, small object near a huge object like a planet, and F sub G is the much more generalized form, which we will get to in chapter 9, I believe. All right, another conservative force.
Electric.
There's one. That's right, and you had also said magnetic. And I think they probably listed one more.
Elastic?
Yeah, elastic. And I put a subscript S for spring, just because I'm using E already for electric. Now, every conservative force has a potential energy formula. So mgh is it for weight, negative g, mass 1, mass 2 over r is for gravitational force, spring 1/2 k delta x squared. And those are the three that we primarily will deal with in this course.
Let's see, Mike, going over all that again.
These are all examples of conservative force. Every conservative force has a potential energy formula associated with it.
We're talking about all the way from what we was talking about.
Right here,
Yeah, what does that say right
a
there?
conservative
Oh,
force,
that's Going far then.
a conservative force will do conservative work. So if that's conservative force, that's conservative work. And conservative work is what will change energy from one form to another. Conservative work will change energy from potential to kinetic or kinetic to potential. Non-conservative work will dump energy into a system or take it out.
Okay. Okay. And then you got this right here.
And then,
These are the-
then narrowing down on just looking at the conservative forces. Not going into the formal definition of conservative force, but more just examples. These are the conservative forces that we'll deal with.
And the first one is what?
This is the elastic or spring force,
Okay,
weight,
wait,
the more general gravitational force, electric force, magnetic force.
okay.
And it's a subscript B
Okay,
for magnetic.
okay.
Because somewhere along the line, someone was coming up with the names, they needed the letters to represent what they were talking about. And magnetism was the second one. The first one he used the letter A for. And last time, did I do an example of an object falling? I can't remember the last thing I actually did. What was the last thing I actually did? The work energy relationships. All right, so we combine work and the types of forces, the types of energy in the three work energy relationships. So total work or net work is the change in kinetic energy. Conservative work is the negative change in potential energy, and non-conservative work is change in energy. And based upon Brianna's notes, that's the last thing we did. All right, so let's actually apply some of this stuff. Get away from the vocab. I have an object. At this point in time, it's moving, so the kinetic energy, I say I've got 50 joules of energy. Based upon its mass and its speed. It has potential energy of negative 200 joules. Nothing wrong with negative potential. What is the total energy? Or total mechanical energy, we could also say. Like we're not dealing with it bursting into flames or anything like that.
Are we multiplying or just adding?
Total adding.
Negative 150 joules.
There we go. And I appreciate that you threw in the units. All right, so we have negative 150 joules.
Oh, yeah, I get 150 if that's 200 joules, right?
That's a negative right there.
Oh, okay, my fault.
No problem. A conservative force acts on it. So you can imagine that there's gravitational force acting on it, or a spring is pushing, ideal spring is pushing against it. A conservative force acts on it. So conservative force acts on it, does work on it. I like that wording better. Conservative force does work on it. And after that, the potential energy is now negative 100 joules. What is the kinetic energy?
Maybe 100?
50 joules.
It's not,
Is this a different problem?
no, it's the same problem. I do realize that I do have an issue here, so I'm gonna make the potential energy negative 400 joules. And I'll explain why I changed that, once we answer this one.
What is Connecticut? Well, I said 100 the last time, but now it's at 400?
K is not, no, it's not 400.
Is it negative 150 joules again?
It is not. All right, so let's back up over here. So I have this object, I have a conservative force acting on it. I guess if I should specify only a conservative force. So what is the work done by a non-conservative force in this problem?
Negative 200 joules.
250.
All right, so I heard negative 200 and negative 250. Reasoning?
So non-conservatives, the change amount of energy, so I, did like negative 200 and then negative 400 and what you have to like add to it.
And Brianna, did you have?
I don't know, it's just what the difference is, so getting my best guess.
Okay. If I have only a if I have only a conservative force acting on the object, what does that mean in terms of non-conservative forces?
They're not acting on the object?
Say it again?
They're not acting on the object?
Okay, right. So if there are no non-conservative forces, what is the non-conservative work being done?
Zero.
And if there is no non-conservative work being done, what's the change in energy?
Zero.
Zero. If the non-conservative work is zero, change in energy is zero. So what's the total amount of energy? After the conservative force does work on it, what's the total energy?
Negative 400 joules.
Wouldn't it be just the same?
As?
Negative 150?
Exactly.
Oh, it's the same.
Conservative forces conserve energy. The total energy stays the same.
That's because it's conservative force?
Yes. Called conservative because it conserves energy. So, what is the kinetic energy? I know I have negative 400 joules of potential. I know my total is negative 150.
250 joules.
How'd you guys get that?
Negative 400 plus what gets you negative 150? That's the math problem. So you add 400 to both sides. That cancels out on the left side, and on the right side, negative 150 plus 400 is 250.
And is it 250 positive? Always, is it always a positive number for kinetic?
All right, let's talk about that, because that actually segues into the mistake I made before. Originally, when I said, I think I said U is negative 100. If the potential energy was negative 100 joules, what would the kinetic energy have to be?
50?
I might have missed a word.
No, just a 50.
No, not 50,
Negative 50.
negative 50. Because when I add them together, I need to get negative 150. All right, so, seems like you did this last time. I'm about to ask you what the formula for kinetic energy is. And you're gonna respond in the chorus of angels. So, look up if you need to.
1/2 times something.
All right. We're gonna do it in unison,
Oh, sorry.
giving people a chance to get there. If somebody has it, you wanna, some people are still looking. Are we ready? What's the formula for kinetic energy?
1/2
mv squared.
That was nice. I'm hoping